For an introduction to atomic nuclear physics, we're going to discuss some of the basics of the atom, as well as we will take a look on how half-lives work. So an introduction to begin with, we are focusing on what we call subatomic particles. So we are talking about things that are smaller than the atom. As you probably know from middle school, atoms are composed of protons, electrons, and neutrons. Protons being positive, P+, electrons being negative, E-, and neutrons being neutral, N0. The protons and neutrons are in the nucleus, and the electrons orbit outside. You're looking at the Bohr model of the atom. It is technically incorrect, but it's a good model for us to take a look at for everything that we are concerned about. So if we were to think about our classroom that we would normally be in, a question I would ask you, is the room made of more matter or is it mostly empty space? And the answer, surprisingly to a lot of people, is it's mostly empty space. If you were to take an atom and expand it to the size of a football field, a ping pong ball dropped at the 50-yard line would represent the nucleus, and then the tip of a ballpoint pen would overdramatically represent the size of an electron that's orbiting the football field in the stands. So it's mostly empty space, which means the nucleus is incredibly dense. Now, some terminology for you: atomic mass, atomic number, isotope, ions. Those things are going to pop up quite a bit. We are not going into a chemistry level of detail. So, for example, if you looked at the periodic table for carbon, you would probably see 12 point something or another with a few decimal places. We're going to keep it simple, and we'll have carbon 12, carbon 13, carbon 14. The mass of carbon 12 is 12. The mass of carbon 13 is 13. The mass of carbon 14 is 14. What chemistry does is it averages the isotopes that we have found on Earth. But ultimately, the atomic mass can be determined simply by adding the number of protons and neutrons. We do not care about the number of electrons because the number of electrons is, well, irrelevant to the mass, because electrons are about 1/1000th to 1/10,000th the mass of a proton or neutron. The atomic number is a specific count of the number of protons. So if you look at the lower right, isotopes of carbon, C12, C13, C14, all three of those have 6 protons. If they have 7 protons, it is no longer carbon. If it has 5 protons, it is no longer carbon. Now, what is C12, C13, C14? What is changing is the number of neutrons. The carbon 12, since it's carbon, must have 6 protons, and therefore, since it's 6 plus X equals 12, it would have 6 neutrons. Carbon 14, since it's carbon, must have 6 protons. 6 plus X is 14. X would be 8. You have 8 neutrons. Ions, just for terminology, ions are when electrons are added or removed, making the atom electrically imbalanced by giving it either a positive charge if we remove the electron or negative charge if we add an electron. This unit is not going to focus on ions, but I did want to talk about it to clarify what's the difference between an isotope and an ion. A bigger focus in particular for this learning engagement is going to be on half-life. The definition of half-life is right there on the screen for you. The amount of time required for half of a sample of radioactive substance to decay into a new substance. So, for example, the half-life of carbon-14, which is what we use for carbon dating, you've probably heard the term carbon dating, is 5,730 years. So if we find a bone that has half of its natural carbon-14 in it, since carbon-14 is radioactive, it will decay over time and turn into a different element. In particular, it turns into beryllium. The carbon-14, since half of it is left, we would say that particular bone is 5,730 years old. Another example is if we looked at the half-life of a substance and you're told it's 20 minutes. And if you have 100 kilograms of that substance, after one half-life you would have 50. After the second half-life you would have half of 50, or 25. After the third half-life you would have half of 25, or 12 and a half. And it goes on and on and on. The parent or mother atom is the original atom, and the daughter nucleus is what it has decayed into. Another example showing you here, if the substance has a half-life of 30 seconds, what percentage remains after 90 seconds? So 30 seconds is one half-life, 60 is two half-lives, 90 is three half-lives. You are down to 1/2 raised to the power of 3, or 1/8. At the bottom of the screen you see something that has a half-life of 86 years. If you started with 100 kilograms, after 86 years you would have 50. Well, what happened to the other 50 kilograms? It's turned into a new element. It didn't just disappear, it's a new element. And we'll talk about how we get those new elements later. Another example, fluorine-21 is a half-life of 5 seconds. What fraction would remain after 1 minute? Well, that seems like a lot, because 5 seconds is 1, 10 seconds is 2, 15 is 3, on and on and on and on and on. Well, there's an easy way to do it. We use 1/2 to the power of n. Well, how many half-lives went by? Every 5 seconds there's one half-life. So in 60 seconds there will be 12 half-lives. Take 1/2 and raise it to the power of 12. You would have 1 over 4096 remaining as a fraction of the original substance. Carbon dating is used a lot, in particular with humans and ancient civilizations. This is how we know things like humans began to move into Mesopotamia and the Nile River Valley around 4000 BC. It also tells us things such as the oldest shoes created by humans come from about 40,000 BC. So how is carbon-14 created? Well, carbon-14 is actually created in our atmosphere. We have a lot of carbon-12, and the carbon-12 is there because there's carbon dioxide in our atmosphere. So what happens is, due to the sun sending out subatomic particles to the Earth, sometimes when they collide with our upper atmosphere, the carbon-12 gets converted into carbon-14. I won't go into too much detail about that, but you could look it up if you're curious. So where does the carbon-14 go? Well, plants use carbon-14 in order to conduct photosynthesis. They use carbon dioxide. They don't really care if it's carbon-12 in the carbon dioxide, carbon-13 in the carbon dioxide, or carbon-14 in the carbon dioxide. So how does it get to the human? Well, either the human eats the plant or an animal eats the plant. Either way, if the human eats the plant, the carbon-14 is in the human. If an animal eats the plant, the carbon-14 is in the animal. And then the human eats the animal, therefore the carbon-14 is now inside the human. Some of it does get discarded as waste, but some of it does end up in our bones. Now, argon dating, for example, is used for rocks, and the reason is carbon-14 has a half-life of 5,730 years. If we're talking about the Earth, which is about 4.5 billion years old, carbon-14 isn't going to work, because after so many half-lives it just becomes too inaccurate. We don't date dinosaur fossils by carbon-14. 65 million years ago is far too long to use carbon dating. We use argon dating for rocks and for some fossils, and we get away with this because argon's a noble gas. The trick in argon dating is that any argon found inside of a rock had to have come from a nuclear decay. When that rock was first created from lava or magma and it cooled, the argon, which is a gas, would have evaporated out of the rock. So therefore, there would have been no argon inside the rock. Over time, things decay into argon, and the argon is trapped inside the rock. Now, another thing that people would ask, Well, how do you know there wasn't argon in the rock to begin with? Perhaps it wasn't a molecule. For example, hydrogen is found inside the human body because we drink water, and water is hydrogen dioxide, hydrogen, H2O. So there's definitely hydrogen inside of your body. It's in a molecule, though. Well, argon is a noble gas, which, long chemistry story short, it means argon would never exist as a molecule. It is impossible for it to exist as a molecule. Some other things that we do use nuclear decays for are tracers and MRIs. If you've ever had a CAT scan or an MRI, they put a radioactive chemical into your bloodstream, and then that chemical will begin to decay, and these charged particles will stream out of your body, and then the magnets inside the MRI machine will direct them and form an image, similar to how a camera directs photons of light to form an image onto a piece of film. There's some other purpose for it, for example, nuclear fallout, radioisotopes, and we'll get into more details about this in some future lessons, but I've gone for a decent amount of time and I kind of want to stop this video. You can go ahead and take a look at this slide if you want to see some other applications, but I am going to end it here.